Okay, let's go ahead and get started. So first, I want to respond to the questions I've gotten about the exam. That exam I'm going to move back or push to at least probably not next Thursday, but the Thursday after that. Okay, so you don't have to work on the exam today. Ignore the due date for that. It will change. In fact, I'm probably going to switch the format of it a little bit. But yeah, this exam will not be until not next week, but the week after. Okay, that way I can give everyone a review and send out a document for you to kind of like practice on over the weekend. So please don't worry about that. So today we're going to look at cardinality of sets. From what I can gather from your course material, it looks like you just went over sequences and functions and a little bit of series maybe. So I'm just going to go ahead and pick up with cardinality of sets, okay? And this should finish off a lot of chapter 2, and then starting next class, we'll pick up on chapter 5, which has to do with algorithms, okay? So as I'm lecturing, feel free to speak up if you have any questions. I'll stop, I'll answer anything you want. So let's go ahead and get started. So, all right, cardinality of sets. In particular, all of you should be familiar with what the cardinality of a set is. It's the number of elements in that set. But we haven't really talked about the infinite case. Okay, so infinite sets. So how do we measure the cardinality of an infinite set, right? So imagine, for example, you have like 20 seats in a room, right? So you have 20 seats in a classroom, and there are 20 students that come in and fill up each of those seats. And for every seat, there's exactly one student. For every student, there's exactly one seat. So then we would say that these two sets have the same cardinality. So we're going to use that notion to define the cardinality of infinite sets. So definition. Okay, so the sets A and B are said to have the same cardinality so i.e. cardinality of A is equal to the cardinality of B whenever there is a bijection from A to B. Okay. So a bijection, if you recall, is a one-to-one function. So this often is referred to as a one-to-one correspondence. And so a one-to-one function from A to B. So an injective and surjective function from A to B. Okay? So we can use this to measure the cardinality of infinite sets as follows. So, for example, the set of odd positive integers has the same cardinality as the positive integers. Okay, so this might seem a little bit strange because it almost seems like the odd positive integers make up half of all of the positive integers because you have either odd or even integers, right? But it turns out that they have the same cardinality. It's, by way of this definition of sets having the same cardinality. So to show this, we can kind of sketch out a proof. So let's say I'm going to denote this set here of odd positive integers. I'll just call that like z odd plus. So z subscript odd with the plus. So let f map z odd plus to z plus positive integers be defined by, or actually, let's go from z plus to z odd. Yeah. Be defined by f of n is equal to twice of n plus 1. Okay, so in order to show that this set and this set have the same cardinality, we need to show that this function is a bijection from that set to that set. Okay, so in order to show it's a bijection, we have to first show that it's one-to-one or injective, and then show that it's onto or surjective. So let's say, so part one, I guess, show injective. Okay. So now this would be the case that to show that a function is injective, you assume that f of n is equal to f of m, and then show that n must be equal to m. So assume f of n is equal to f of m, defined by that function. So then 2n plus 1 is equal to 2m plus 1. But this implies that 2n is equal to 2m. And so 2n is equal to 2m, i.e. n is equal to m. Okay, so under this assumption, if the outputs or the images of n and m are the same, then it must be the case that n is equal to m. So yes, this function is injective. So far, so good. In part two, we need to show that it's surjective. So to show that this function is surjective, we just need to pick something in the codomain and then show that there is something in the domain that is mapped to it by this function. So I don't know, choose x kind of arbitrarily, not kind of, but just say pick an arbitrary odd positive integer. Then by definition, right, since it's odd, so we know something about what x looks like. So then by definition, There exists an integer k. So there exists an integer k. So that x is equal to 2k plus 1. Right? So since x is positive, we know that k is positive, right? So since x is greater than 0, we know k is greater than 0. That means that k is in z plus, so it's a positive integer. And then we can just say hence x is equal to 2k plus 1, which is equal to fk. Okay. So what we've shown is that we picked an arbitrary odd integer, and then there exists a k in the domain of the function that gets mapped to that arbitrary odd integer by that function. So it is surjective. Everything in the codomain has a pre-image in the domain. Okay. So what this shows us is that, like altogether, this says that the cardinality of the positive integers is equal to the cardinality of the odd positive integers. Okay. Now, a similar argument would show that the set of even positive integers has the same cardinality as the positive integers. So, okay, what does this say in general? Well, if you think to what it means to have a one-to-one correspondence or a bijection from two sets, it means that we can list them in pairs. So, for example, so the positive integers look something like 1, 2, 3, 4. Actually, we're including, yeah, 1, 2, so forth and so on. But then the odd positive integers, like this. And now, a one-to-one correspondence means that there exists a function from one set to the other that pairs up each element in the domain and the range, pairs them up uniquely together in some pairing, right? One-to-one correspondence. So here we see that these are paired, 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 these are paired. And this is going to go off to infinity, right? But notice that as far down this list as we can go, that everything in this set is going to have exactly one thing in the other set that's paired with it. So if we just keep on going to infinity, this pairing is always going to happen. So in an infinite sense, these do have the same cardinality. Because for every student, there's a chair. For every chair, there's a student going off to infinity. Okay? So that's the idea behind this definition. It's about pairing up the elements with each other as this pairing process goes to infinity. Okay? So this leads us to an important piece of terminology about the positive integers. So definition. Um, if A is a set with the cardinality of A equal to the cardinality of the positive integers, then we say that A is countably infinite. Okay. If the cardinality of A is less than infinity, or the cardinality of A is equal to the cardinality of the positive integers, then A is countable. Okay, so countably infinite and countable. And this probably leads us to the most important definition. Discrete mathematics is the study of operations on countable sets. So I don't know if any of you encounter this in your day-to-day life, but so like other majors might ask you, like you say, like you're taking discrete mathematics, right? Or like my friends and family might ask me, like, what discrete mathematics is, because I'm always teaching it. And I find that a lot of students forget or don't know the definition of what this course is. They'll say things like logic or algorithms or something like that, but really, at the heart of it, discrete mathematics is defined as the study of operations on countable sets. So that brings me to like another observation. I think like 90% of the students in this course are computer science majors. Why are there so many computer science majors in here? Like, why is it the case that a computer scientist would need to learn discrete mathematics? Can anyone take a guess? Anybody want to guess? Well, the most obvious reason is that computers are basically operations on finite or countable sets. If you think about like what is a computer, it's a finite amount of memory, right? a finite amount of operations that can be done, right? A finite amount of storage, right? The operations used on a computer have to obey the rules of countable sets, countable operations on countable sets. So the reason why there's so many computer science majors in here is because that computers are discrete mathematical objects. And in fact, the first computer scientists were actually discrete mathematicians. They kind of envisioned a computer before there was a computer. Also, algorithms typically perform in a, will perform in a countable list of operations. Even if some of them happen to go on forever and it's infinite, it's still a countable list of operations that can define an algorithm, which we'll be getting to shortly. Okay, so let's look at some more countable steps. Okay, so theorem. The set of positive rationals is countable. Now this should seem strange. Why should it seem strange? Well, if we look at a number line, right, and we just look at like 0, 1, 2, off to infinity, right? So these are like positive integers, right? But okay, just let's look between these two integers here. A half, a third, a fourth, 1/100, right? What about 2/3, 3/4? So an observation here, so observation. In between any two integers, there will be an infinite set of rational numbers. Now that's a lot of rational numbers, right? Like in between any two whole numbers, there's going to be an infinite number of rational numbers. Like you can just start at 1/2, 1/3, 1/4, 1/1000, 1/1,000,000,000, and just keep on going. There's going to be an infinite number of rational points in between those two whole numbers. So that should seem very strange, that the set of positive rationals is countable. Actually, the set of all rationals is countable, but we're going to show the set of positives is rational. I mean, is countable, excuse me. Okay. So, another observation, or maybe a fact, a set is countable if and only if it can be expressed as a sequence. Okay, so recall a sequence is a function from the positive integers to some set, right? So basically, if you can take a set and list out its elements in a sequence, then it's going to be countable because you're putting a one-to-one correspondence between the sequence, a sequence of unique terms. So you're putting a one-to-one correspondence between the sequence and the set. So 1 gets mapped there, 2 gets mapped there, 3 gets mapped there, 4 gets mapped there. That set of positive integers, by creating the sequence, you're putting it in the one-to-one correspondence. So if you write it out in the list, that one-to-one correspondence must exist, so then it's countable. If it's countable, then you can write it into the sequence in the reverse manner. So this is like a very important fact about countable sets. You're countable if and only if you can be expressed as a sequence of unique terms. Okay, so with that idea, we're going to look at the proof idea behind, not the actual formal proof, but the idea behind this proof. So let's write out this grid. So we'll say 1 over 1, 1 over 2, 1 over 3, 1 over 4, dot, dot, dot. Okay, so this sequence here, you can see this is going to contain every rational number with a 1, every positive rational number with a 1 in the numerator. Do you see that? Like the next one would be 1 over 5, then 1 over 6, so forth and so on. Then, so then next, let's look at this sequence. Now this sequence is going to contain every positive rational number with a 2 in the numerator, right? The next would be 2 over 5, 2 over 6, so forth and so on. Let's do another one. Now this sequence is going to contain every positive rational number with a 3 in the numerator, right? In this same like pattern, we keep on going. Dot, dot, dot that way, dot, dot, dot that way, dot, 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 dot. So what we're doing here is we're making a grid, right? This contains all the positive rationals with a 1 in the numerator, all the positive rationals with a 2 in the numerator, so forth and so on, along the rows. And on the columns, we get every positive rational number with a 1 in the denominator, every positive rational number with a 2 in the denominator, every positive rational number with a 3 in the denominator, so forth and so on. So this is a sequence, that's a sequence, that's a sequence, that's a sequence. This grid will make up every possible positive rational number. Okay? If it just goes on forever, this massive grid will do that. So if we can somehow take this grid and transform it into a single sequence, then by doing so, we're putting it into one-to-one correspondence with positive rational numbers. This grid must be countable if we can do that. If we can somehow take that grid and transform it into a sequence. Well, this actually isn't so bad. So let's start here. And we'll call this like A1. And then let's go here. We'll call that A2. And let's go down here. We'll call that A3. And then let's come back around here. We'll call that A4. Now 2 over 2 is going to reduce to 1 over 1, so we don't need that one, so we can just bypass it. We'll go straight to 1/3. So we'll call this A5. Then wrap back around. A6. A7. A8. A9. And what are we doing? We're zigzagging along the diagonal of this grid, avoiding repetition when we need. Actually, even if we didn't avoid repetition, we would still have a countable set. This would still be a sequence. So what this shows us is that once we define this pattern, which we could do explicitly with the formula, but the picture is good enough for now, we see that if we pull this string taut, right, we have A1, A2, A3, A4, A5, A6, A7, A8, A9, so forth and so on. We put that set into a sequence, a list. Therefore, it must be countable, because a sequence is simply a function from the set of positive integers to the set. And there's no repetition anywhere in here. We're good. That set's countable. Now, the same argument holds for the set of negative rationals. And I think it's a part of your homework to show that if you have two countable sets, the union of those sets is also going to be countable, which means that the set of rationals is countable. So even though there seems like there's so many more of these rationals than the positive integers, it turns out in an infinite sense, they have the same size. There's no set that's bigger than the other in that case. Okay? So if these sets are countable, then what would be a set that isn't countable? Well, turns out that the set of real numbers is uncountable. And I think we have enough time to prove this. So we're going to prove this by proving a more restrictive theorem. The open interval from 0 to 1, which is a strict subset of R, right, is uncountable. In another one of your homeworks, I'm almost positive, would be to show that if a subset of a set is uncountable, then the superset must also be uncountable. Okay, so let's prove this. We're going to do this by way of contradiction. So, by way of contradiction, Suppose that that open interval is countable. So suppose the open interval from 0 to 1 is countable. Okay? Now, if that is indeed countable, then we could list out every element in that set, or that interval, right? In a sequence. So, so then, if 0, 1 is countable, then we may list every element of 0, 1 with the following sequence. Okay, so we'll say R1, R2, R3, dot, dot, dot. Okay. Now, notice that every number in 0, 1 has some expansion, decimal expansion, like 0. Like 1/4 has the decimal expansion 0.25000000, right? So every number in here is going to have a decimal expansion. Okay? So when I'm writing this, I'll explain in a second. Okay? So here, Dij is an element of the set 0, 1, 2, dot, 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 to 9. So these are just digits, right? So if R1 was a quarter, right, a fourth, then that D11 would be a 1, that D11 would be a 2, and then that D12 would be a 5, D13 would be 0, and the rest would be zeros all the way through. So basically the first index is which one of these numbers, and the second index is the digit in that decimal place of that number. Okay? So because 0, 1, we're assuming it's countable, we can list out every single one of the elements in there in a sequence. Each one of those elements has a unique decimal expansion. So we can write it like that because we don't know which ones come first, really. So then what we can say, let R equal 0.D1, D2, D3, dot, 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 where DI is defined by this piecewise function, where DI is equal to 4 if DII in this grid is not equal to 4, and 5 if DII is equal to 4. Okay, so those are the digits that go in the decimal expansion of this number are. Okay. So, okay. And I'm going to go ahead and say that this sequence here, I'm going to call that R sub n. Okay. Okay, so that sequence should contain every element in 0, 1. However, so this is a contradiction since the number that we made R is not in our sequence. Done. So why is that the case? Why isn't, so clearly 0 point stuff is going to be in that interval, right? So if this list lists out every number in that interval, this number R better be in there. However, it's not. Why? So let's ask ourselves first, can R equal R1? No. Why? Because D11, this first entry here, that number, if it was not a 4, then our number would have a 4 there. If that number was a 4, then our number would have a 5 right there. So R cannot be equal to R1. What about R2? Well, if D22 was not a 4, then our number would have a 4 right there. If D22 was a 4, then our number would have a 5 right there. So that entry would be different than that entry. Our number couldn't be R2. By the same reasoning, R cannot equal R3. So forth and so on throughout the entire sequence. R cannot be a part of that sequence, which leads to a contradiction since this sequence contains every element of that interval. However, R is also in that interval, but not in the sequence. That's a contradiction. Done. So that must be uncountable. And if the subset of that set is uncountable, then the full set is uncountable. Okay, so that will be it for today's lecture. I will see all of you again on Thursday, and I will post some type of announcement to Blackboard about the exam schedule and things like that, once I finally get the dates changed. Okay, so everyone stay safe. I will see you next time.